first lecture today, the first lecture of the school, is by Thibault Damour from the IETS in Paris. And Thibault, of course, is one of the world's experts on how to make predictions from general relativity, from the equations I discussed this morning, and which he will review and then tell us a bit about how to turn those equations into experimental predictions, and I think also discuss a bit the current state of verification, experimental verification of general relativity. So it's a great pleasure to introduce Thibault Damour.
Thank you, David. So let me start from scratch. So very quickly, special relativity is a theory where we have a rigid structure of space-time, which where you have points in space-time, and between 2 points, even if they are very far apart, you can associate to 2 points vectors that live in a vector space. So this is an affine space. And then on the vectors PQ, you have a quadratic form, which is usually denoted eta. Okay? And this quadratic form, which I will just denote by a scalar product, when you use a special frame called Lorentzian frame, where this is represented along a set of vectors that you choose appropriately, this thing takes the quadratic form eta mu nu. So let's say it's the difference between 2 points, so it would be delta x mu, delta x nu. And this is a diagonal matrix, which is, I will take the signature mostly plus. So in 3 plus 1 dimension, it has 3 plus 1 on the diagonal and 1 minus 1. And more generally, in capital D equal small d spatial dimensions plus 1 time, there will be small d plus 1s and a minus 1. Okay, and when you take this, you usually call this delta S square, the interval square between 2 points. And now pictorially, this means that the structure of this affine space has a homogeneous structure. So around each point, there is this quadratic form, which there is the set of points such that the square interval is equal to 0. There is the set of points where the square interval is equal to, let's say, plus 1, which is an hyperboloid, and the set of points where this interval square is equal to minus 1. And this figure, which is the geometry of Minkowski space, is repeated in an homogeneous and perfectly regular manner all over the 4 dimensions of space-time. So this is special relativity. Now, general relativity is a theory where this homogeneous simple picture, everything is the same everywhere and every when, is now deformed into something which is called curved space-time or deformed space-time. But the basic definition of general relativity is that at each point, if you look at the infinitesimal neighborhood of each point, you will have the structure of special relativity, which means that there exists no longer the notion of vectors between 2 faraway points, but the notion of vectors always exists between a point P and an infinitesimal, a point which is infinitesimally near. So you have the notion of local vector dp, and which, when you use arbitrary coordinates to represent the 4, let's say, dimension of space-time, will be represented by 4 numbers. And then if you, I will define a little bit later what are the various bases of vectors in space-time. If I use natural coordinates, I have a natural set of vectors associated to that. And then there exists what replaces the special relativistic squared interval is an infinitesimal square interval between this point P and its neighborhood point, which is given by a quadratic form on dp, which means that in coordinate at each point x, we have no longer those constant function eta, but some general quadratic form in 4 variables with locally the signature minus plus plus 1, which means that if I look at the set of points around P where, let us say, ds square is equal to plus some infinitesimal plus epsilon square, some positive infinitesimal distance, then it will locally look like this. But curved spacetime means that around each point, this structure is, continuously deforms as you move from one point to another point. Okay? So instead of having something well ordered, you have something which is a distorted version of this. And now the technical question is this is called the pseudo-Riemannian metric of spacetime. And if I change coordinates, so this is in a set of coordinates here in spacetime which are arbitrary, while here in special relativity there were spatial coordinates, so-called Lorentzian coordinates, where the metric was taking this form. If I change from the coordinates x mu to arbitrary new coordinates x prime, which depend continuously on x, then this quantity is invariant, which means that g mu nu of x point is obtained from the new coefficient in the new coordinates x prime by just d x prime alpha over d x mu, d x prime beta over d x nu, where x prime is a certain function of x nu, an arbitrary coordinate transformation. These functions vary like that.
So before we go on, can people in the back read the blackboard? Whoever can't read the blackboard, raise their hand.
Should I write bigger? Yes, okay. But maybe, are there people who, I won't go long at this level, but is it useful for some people, or you all know that by heart? I continue a little bit. So now let me define as a physical theory general relativity. General relativity is defined by 2 basic postulates. One postulate which concerns the coupling of matter to gravity, and the other postulate which is what is the kinetic term, the term in the action which describes the propagation of and the self-interaction of the gravitational field itself. And today we will discuss the first basic postulate of general relativity, which is the coupling of matter to gravity. Okay. And this was the new fundamental idea of Einstein, that this coupling can be summarized in the phrase that gravitation is identified to space-time geometry. And space-time geometry will mean this structure. So let's say essentially, so the gravitation is described by this g mu nu of x lambda field. And by the way, it is a historical accident that geometers had used the letter g for geometry, for the metric g mu nu, but it was a well-chosen notation because g will also be gravity for Einstein. Okay. And now, the first postulate is defined by the phrase that this thing will couple, so it's also called the equivalence principle, but let's define it more precisely, couples universally and minimally to all the fields of the standard models, okay, to the fields of the standard model, which means for me matter, okay, but in a concrete sense. So what does it mean? For this, we will take the structure of the Lagrangian of the standard model. So the Lagrangian of the standard model is usually, is written by definition in special relativity, and therefore it contains, to describe the embedding of the fields in space-time, everywhere for instance, the kinetic terms of the various fields are defined with this special relativistic metric eta. And when you write a kinetic term and you have a certain field, which may contain several types of indices, it can contain internal indices, if it is like a SUN multiplet, and it can contain also some, let's say, vectorial or tensorial indices, if it is a vectorial gauge field. And then you act on it with a certain space-time derivative to define kinetic terms. So the two objects that we need to generalize to define the coupling of gravity to matter is to make clear how you change eta mu nu everywhere and how you change the derivative. Now, by definition, the first element of the coupling will be that everywhere eta mu nu will be replaced by g mu nu. But this is not enough, okay? So let us be more concrete. The structure of the standard model Lagrangian, which means the term that you integrate over space-time, is something which depends on fermionic fields, psi, on vectorial gauge field, which contains some internal indices, on the Higgs doublet, sorry, I should say the H boson, the broad angular Higgs field. And then we want to couple this to g mu nu. Okay, this means functional dependence that will include derivatives, but that will be a local action. So, for instance, the gauge fields usually in special relativity, the gauge fields, the kinetic term is -1/4 of f mu nu square. Okay, and then you make a sum over the gauge indices. So the square here meant square with respect to eta mu nu. Now, what happens in general relativity is first you need to include the square root of the minus the determinant of g. So let me define g as minus the determinant of the matrix g mu nu. It's a function of x. Okay, usually g means the determinant, but then you have to write square root of minus g because g is negative. So it's better to put the minus sign in the definition. And this object is such that square root of g d4x, let's say if I am in a 4 space-time dimension, or d dx, is a volume element which is independent of the coordinate system you use, that you can prove by the law of the transformation of determinants and the fact that you have this law of transformation. Okay, so this is a Lagrangian density that I will integrate over d dx, over the full space-time. So we will need the square root of g. Now, we want something quadratic in some gauge field, let us say this, which has some gauge index here. The gauge index will be traced over by an invariant matrix in the Lie algebra where this lives. And now we want to take a square with respect to the g mu nu. So this means now replacing eta mu nu by this. Okay? So this is the first element where you define the standard model Lagrangian by replacing eta mu nu by g mu nu. But I need also, I will define just below what is this in curved spacetime. Let me write the rest of the Lagrangian. I discuss a little bit more detail the fermionic coupling because it will be useful for the lectures of Hermann Nicolai. So this is the kinetic terms of the fermions, and inside this object that I will define now, there is also the gauge connection and the gravitational connection. So all the information will be in the definition of this object and of this object here. So for the H boson, you have also a special gauge derivative for the H boson. And you replace the square of the gradient of the H boson by a g mu nu here. You replace eta mu nu by g mu nu. And you have the potential of the H boson. And then you have the Yukawa couplings, which are, again, a square root of g, sigma h psi, where the internal indices of the Higgs doublet are coupled to indices of the psi. Now, I have defined square root of g. Now, let me define the various derivatives, because here, for instance, if I have a U1 gauge connection, we all know that f mu nu in general is just the curl of the gauge vector. if I have a gauge vector for Young-Mills fields, there is an extra term which, depending on how which contains a gauge coupling G. So again, this is a nice historical accident that the gauge coupling is denoted small g, because we know that in string theory there is a really big unification between the gauge coupling G, between the G of geometry and the G of Einstein. Okay, so notations sometimes are good. And here there are structure constants of the Lie algebra, in which this is an infinitesimal element of the Lie algebra. And now here there are derivatives, but here it is a curl. Because it is a curl, as we will check in a moment, this object is a good tensor of space-time, and I don't need to modify this derivative here. Okay? So the minimal coupling means if I don't need to do anything, I don't do anything. But because, yes, so for people who have never heard that, what is important is here in this curved space-time, when I have 2 points, a vector means always something, a tangent vector to the manifold means something which is proportional to an infinitesimal displacement. So a vector is really always you go from one point in space-time to an infinitesimal point nearby. And a vector will have components upwards, like coordinates. And if you define something which is a linear form on vectors, something dual to vectors, something that I can contract with a vector with an index up to get a scalar, then this is called a covector or one form, and A mu is of this type. So if I have a vector with an index up, and which varies by, when you look at what it means, it varies by one matrix like that, then I define a covector or one form by being something dual, so this is invariant. Okay. This object is of this type down, one form. Now, let's go to the connection. For the Higgs field, the connection, because Higgs field is a scalar, so in general, the derivative contains the derivative of the scalar, and then you have a term coupling to the various connections that its object is linked to. So let me remind you of what is a general connection. We all know that for U1 for electromagnetism, the rule is that you replace d mu by d mu minus I e a mu, okay? Where E is the coupling of to the electromagnetic field, and a mu is the gauge field of electromagnetism. And we all know that this new definition is such that I can, this acts on an object like psi, which can vary by an arbitrary phase factor at any point. And then, if I want this to be a symmetry, a local symmetry that can vary at each point, then I need to add an extra term, and this term will vary under a gradient of this object. By the way, also another historical remark. Actually, gauge theories were invented after general relativity, and the motivation of Hermann Weyl, who introduced them, was precisely because in general relativity, each point of space-time lives an independent life. Here in special relativity, everything is rigid and connected. In special relativity, you know, a point here far away is disconnected from this point. And then this is why he introduced that there could be not only this curved space-time disconnection, but also extra scalar things, U1 things. And in general relativity, it is very natural to have local gauge symmetries, and certainly not only global gauge symmetries. So when you have an object of this type, so in general, this was for U1, okay? U1 meant I have only a phase factor, which is in the U1 group, acting on this object, and the corresponding gauge field has no internal index, it has only one. When you have a transformation which is like in SUN, so here you have a matrix instead of this object, and the gauge connection contains an extra term where this object lives in the Lie algebra of SUN, but the object you talk about rotates under SUN in a certain way. This object is not itself in the Lie algebra. It is in some so-called representation. It is in some vector space which is acted upon by SUN, and these are the matrices that represent the action of SUN on this. And the gauge connection always contains, besides the ordinary derivative, a gauge field and then a certain matrix representation. Now, for something like a scalar, you again prove, like the curl was here, that this object is a good covariant object in spacetime, and that the square here is a good invariant of spacetime. So I don't need to do anything here. But now let's discuss the Spinor field, for which one needs to do something. First, there is this gamma mu. Here, we are going to discuss now the theory of spinors in curved spacetime. But pragmatically, I define the gamma mu here by something such that when I take the anti-commutator, so these are 4x4 matrices, okay? And the anti-commutator of two matrices, instead of being equal to 2 eta mu nu, sorry, here maybe it is impossible to see, is equal to 2 g mu nu. Can you see here? Yes, okay. But now the question is about what means d mu of psi. So d mu of psi will contain two types of terms. I mean, three types. It contains the ordinary derivative. Psi in general is acted upon by some gauge field. I mean, it can be an SU2 doublet and SU3 triplet. So there will be a gauge derivative acting on it with the gauge coupling associated to the field A and the vector field UA and the representation under which psi rotates. And by the way, it is usual in physics to write these things with minus I, okay? There is a minus I if you want this matrix to be Hermitian, okay? But in mathematics, it is usually better to work with anti-Hermitian matrices. So this means absorbing the minus I in the matrix T, so that when you take the commutators of two matrix T, you don't have an I on the right-hand side. Everything is real, because the structure constants of those real Lie algebras are real and not, they do not contain an I. So we can also forget about the minus I. One can also absorb the G geometrically in the definition of A, okay? So that a better mathematical representation of this would not have the minus IG, but just a plus, okay, and the T. But now let me introduce, so here I just reminded you that you need this gauge coupling because you want to be able to act when you have a field psi which lives at each point of spacetime. At each point, you want to be able to act on it with some matrix, let's say, of SUN, independently at various points. And because of this, you need this term. Now, in general relativity, a spinor is also a representation of a group linked to gravity, which is not the group of local coordinate transformation, but the spin group, which is a covering of this that I will define just in a second. But I just want to say that there will be an extra term here, which is because gravity varies from point to point, I need also a connection acting on psi due to gravity. In this connection that now I will define in detail, I will just write that it has this structure, sigma alpha beta psi. It has the same structure as this one. There will be a field omega which has a last index mu, and which is the connection for infinitesimal displacements in the dx mu direction. And this field here was a matrix in some representation here. The matrix will be defined by this sigma, which is a product of Dirac matrices gamma. Okay? So what is the best way? Okay, let me start here. So let me define this general notion of gravitational connection. So I'm still here. I want to define the basic postulate of general relativity, which is that to write the standard model, I need to replace the special relativistic metric by G mu nu, and I need to replace d mu by the part of it which is not the gauge connection, the usual gauge connection, but the part gravitational, by some derivative that I want to define, this nabla mu, gravitational connection. So what is the general, why do we need in general a connection? If I have a general space multi-dimensional space, but I represent it just by a line, where each point is a point x, and here it is another point x prime, which may be far from it. The framework in which you need a connection is when above each point, that is to say, associated to a point in space-time, you want a vector to live at this point of space-time. So the vector space, which I will call F for fiber, is the space of all the vectors that you can live at this point x. Okay? And the problem is that when you have a curved space-time, above each point, you have like that a vector space, which means that if I define, so this is a vector bundle. It's the general definition of a vector bundle. At each point of a curved space-time, I define a vector. So it means above this point, for instance, I have a certain element v of x, which is an abstract mathematical vector which lives in the vector space F. And at this point here, I have a different v of x prime. Okay? And you want to be able to compare this vector to this vector. Another important element for this vector bundle is that there exists a group G acting on so-called fibers. That is to say, there is something which acts on the vector at each point and transform it by an element gamma belonging to this group in a new vector gamma v. Okay? Which, for instance, if I'm talking about a fiber where the local group is SUN, it means I have a multiplet psi with n components, and I act on it with a matrix n by n, and it changes this by a group element. Okay? And I want to be able to act with this group at each point of space-time, and I want this to be a symmetry at the end. So I need to do something in order to write a kinetic term for this object, that is to say, to know how to differentiate it. And the basic idea of a connection is that I need to know what is, in a sense, what is called the parallel transport of this vector here at point x to its parallel analog at point x prime, in the case now where this distance is infinitesimal. Okay? The vector bundle exists globally, but now I look at two infinitesimal points. And to define a gradient of a vector, I need to make the difference between this vector here and this vector here. But you see, they don't live in the same vector space. So to be able to make the difference between vectors in two different vector spaces, I need a way to say which point here corresponds to which point here. And this is called the connection. Now, and the general, now technically, which means that at the end, I will define what is called the covariant derivative of a vector field in an infinitesimal direction dx, which means, okay, dx mu in some coordinates, will be, of v, will be the field at point x plus dx minus the field at point x, which I parallel transport from x to x plus dx. Alternatively, if you want, you can parallel transport this vector back here and then make the difference there. This is to second order, is the same thing. In coordinates, this will define a certain operation, nabla mu acting on v. And the general structure is the following, let's say technically, is that the fact I said that this vector lives in a vector space means for a physicist that it has a certain index. Okay? It is in a certain vector space with a basis and just an index. Now, this index in general is a multi-index in the sense that you could think that this index contains several indices at the same time. It can contain a doublet index. If it is a doublet of SU2, this is an index that takes two values. If it is a multiplet of SUN, let's say fundamental, it means it takes n values or more complicated thing. And in addition, it can contain like tensorial indices. Maybe this thing is also a vector, so it has maybe a mu or it has several tensor indices. Okay. Anyway, at this stage, it's just an index, and what is called technically the connection is to say that I want to augment the ordinary space-time derivative, okay, by an extra term which will be what? So this extra term will have a mu index because this thing is associated to the infinitesimal direction in which I take the derivative. So it will contain like this index mu here and this index mu here. And then it will also contain something that makes a rotation of this object its own space, okay? Which is, it's part of this group here, which is acting. So therefore, it will be a matrix here with respect to, I mean, you need to introduce indices, and then it acts on VB. Okay. So this is the general structure of a connection. It's universally true. And you can just see that all these things are special examples of this. Okay. That and this is the general definition of omega mu. Now, technically, one can also, I mean, mathematicians would simplify the thing by saying, let me compute now, let me define nabla as being the directional derivative of this nabla mu along a certain dx mu, and which means I just contract this by dx mu. So it gives nabla v, which has this index A, is dx mu, d mu of acting on something. You know that this is denoted d acting on something. Okay, it's just the ordinary derivative, but it is also Cartan derivative with the usual technology. You know that d square equals 0. If you don't know this, don't worry about this. It's just to introduce the notation that is this thing. And then if I contract this by dx mu, it is natural to define this object as being omega mu dx mu. So the basic connection, as I said, is a matrix in some internal space, and then it has an extra mu index. If I contract this mu index by an infinitesimal vector, this is what Cartan calls a one-form omega AB. And then there is this form. But now, if you're a mathematician, you don't like to write indices, so you can even say, okay, so a covariant derivative, a general connection is that I have V in some vector space, and it is defined by taking the ordinary Cartan of dV plus an object which is, so I will still add something. There is an abstract object omega, and I have a representation of this object in so that it can act on the vector space on which V lives, because there is an abstract group G, but this group G, think of SUN, is acting, for instance, in the fundamental representation of a multiplet of n things in a certain way. So it's called explicit matrix representation. So there is this abstract object in the Lie algebra. So this would be now in the Lie algebra of G, but as a one form. So it's, let's say, tensored by dx mu. So this is this connection object. And then I mean, there is an abstract connection, and you represent it so that it can act on the tensor indices of it. So that would be the most abstract definition of a connection, but we will work with the more concrete thing here. And let us apply this to... So what are the objects in a curved space-time that we want? What are the vector bundles we are talking about? There are several vector bundles. The objects that we live in a space-time can be vectors or tensors, okay? I can have a vector field, which means something of this type, where this v mu varies when I change coordinates like a dx mu, which means that if I change coordinates, it varies like that. Yes? Yes?
Why you distinguish the Greek and the Latin indices? Why?
Yes, good question. At this stage, the Greek and the Latin, sorry. Yeah, the Greek indices are space-time indices for me. Mu, nu, alpha, beta. They will take, let's say, in ordinary space-time 4 values, 0, 1, 2, 3. The Latin indices here are indices of, let's say, in that case, SUN, okay? This is in the Lie algebra of SUN. So, for instance, if these are the gluons, this would take 8 values. So I use here Latin indices for internal groups like U1, SU2, SU3 of the standard model that act on internal symmetries, gauge symmetries, and I reserve Greek indices for space-time indices that take 0, 1, 2, 3 values in ordinary space-time. Is it clear? Yes, I will keep this. Yes, and now this index was like a more general thing. It could be, that's why I said this thing is a third type of index, which could be a mixture, and we are going to give examples. This index here, capital A, could be either a small a, an internal index, or a tensor index, or a Spinor index, or all of them together. It's just that the connection is, once you see this, this is the universal way of thinking of connection, okay? All these things are particular aspects of connection. And they look different because they look more complicated here. You have a G, you have a T, okay. But if you think it's just a matrix acting in some vector space, okay, which can contain tensor indices, Spinor indices, or internal indices. And then there is a special index mu, which is always a mu, because this is infinitesimal displacement in space-time. This is a connection.
So it's some universal formula.
Yes, that's the universal formula. And I was writing it at the most abstract level and at, let's say, semi-concrete level, because now we are going to make this very concrete. I'm going to discuss when this object is a vector, a co-vector, when it is a spinor, etc. What is this object in this concrete sense? So let me do that now. If I have what is called a contravariant vector in space-time, this is a field at each point of space-time, which, when I change coordinates, vary as if v mu was dx mu, an infinitesimal displacement divided by some scalar, okay? And this means that if I change coordinates x to x prime, it varies this way. And here I am using a convention which was used long ago by Lichnerowicz, which is useful to have in mind, is that when you start changing coordinates, you have the old coordinates, x mu, and the new coordinates, x prime, okay? But it is convenient to keep the same indices, and instead of saying that I have x prime with some new index alpha, you can say I have coordinates x mu prime, which are certain function of the x mu, with the understanding that mu prime is like a different index of mu, okay? It allows not to multiply indices. So I can use mu nu lambda, again, mu prime lambda prime. It's just that it makes things faster. You see, I can write immediately that v mu prime up is dx mu prime up, because it is up, so I put it up, then dx mu down and mu down. If you don't like it, you write it lambda if you want, okay? But it's the same formula. It's just a way to remember. Now, a vector that lives, which is a covector, which is dual to this, such that the contracted product of these two things is an invariant. By the way, I always use Einstein summation convention that when I have a repeated index, in general up and down, then it means a summation over all the values of this index. So here the mu prime is down, so I can immediately write this. Okay, and if you don't like to see the same index, you change the index, but it is the same formula. It's just a shorthand. Now, let me apply this general formula and say, if I have a connection, what will be its effect if I act on a vector of this type v mu, so a vector field in space-time? Then I want something, v nu, which will be the ordinary, equal the ordinary derivative, okay, plus an object which will have three types of indices. And when you use vectors, so the general notion of a connection of a vector bundle, when it is applied to vectors and more generally tensors, is called a linear connection. But it's just a name. It means it is a connection where the space, the vector space that I put at each point in my curve space-time is the space of vectors at this point. And you remember that vectors at the point of a general curve space-time is like an infinitesimal displacement. So that's why the set of vectors at each point is called the tangent space. It is the, I could say the tangent space, is a space like that. But instead of putting it horizontally, I put it vertically. It's just the space of vectors. It's a vector space at each point. And above each point, I have this fiber of vectors. Now, what is the group acting in that case? The group acting on V mu's is what happens when I change coordinates. And I can see this, that when I change coordinates at this point and this point, I have something, a matrix acting on this index. And this matrix is a general n by n, 4 by 4 matrices, let us say, if I am in 4 space-time dimension. Therefore, the group in that case is GL in the space-time dimension. The general invertible matrices D by D, where capital D is the space-time dimension. Okay, 4 in the usual case. Therefore, the connection will be a matrix acting on this index, and in general, so mu sigma mu v sigma. Now, when one uses the linear connection, in general, instead of using the notation omega, although one can still use the connection, the notation omega, one uses the notation gamma for traditional reasons for this linear connection, even if I am not, by the way, in natural coordinates, but especially if I am in natural coordinates. So this object, you see, as the mu index, which is the differentiation index that I will always put on the last. I'm insisting on this because some people put it first. And then when you push indices down, the antisymmetry becomes, you never know what happens. And Hermann Nicolai tends to put it first. But OK, I put it last. And then here you have something which is a matrix acting on this index. So once you understood this formula, once you understood that the mu, OK, is somewhere here, and the rest must be a matrix acting on this index, you have no choice for writing what the indices. You know, you want to get back this object, and it is a matrix acting on this object. And sometimes, I mean, I like to use sigma when it is a summed over index. So you remember sigma is a summation index. Okay? And when you act on an object which has an index down, you realize quickly that you will have a connection where the indices will be reversed. But now, if you have defined the gamma for this, and if you want this object to be such that the product A nu, V nu is invariant, which means that the covariant derivative of this object can be taken as its ordinary derivative, A times V with this index sum, you find that the matrix you need to put here must be the opposite of this matrix. Okay, so which means here I have minus gamma. And then, so let me I put the differentiation index last. This thing is a matrix acting on this, so there will be a summation index. And then I get back to the index nu. Okay? And you have to keep track that this index is up. So there is an empty slot here. This index is up. And then when you realize this, there is no doubt. When you have an object which has several indices up and down, but I write only one, there is a term which is, sorry, I should not put mu up, lambda. There is the ordinary derivative. And then for each index up, I have a term like that with a plus. So here it means I have plus gamma, lambda, sigma, mu. Mu is the differential index is always last. T sigma mu minus gamma sigma mu mu T lambda sigma. Okay, if you think about it, you will recognize this. So here I am just formally saying if I want to define in general relativity a connection of this general type where the fiber at each point, the vector space on which I act is the space of vector fields, let's say, or covector fields or products, tensor products of these, which is a general tensor field. And I want this to be associated to a curved spacetime with metric G mu nu. And there is a theorem which says, due to Levi-Civita, which says that there is a unique connection, gamma, unique linear connection, gamma of this general type, such that the two following conditions are satisfied. What is the basic object that I have in a curved spacetime in the sense of Einstein? It is at each point of spacetime, I have a quadratic form G mu nu, a tensor G mu nu with two indices down. So it is an object that if I have a connection, I can differentiate by using this formula with two indices down, okay? So the covariant derivative, so when I have g mu nu, I can define nabla lambda g mu nu. It will be equal to the ordinary derivative of this minus 2 term with gamma. Okay, I let you write the indices. You just copy these things with putting indices in the good places. Like, for instance, the first one, I have a sigma here, a nu. Then I have a mu, and the differentiation index will be here. Okay, second term. So the theorem is that there exists a unique connection such that the covariant derivative of g mu nu, which is a tensor, is equal to 0. So this is an invariant condition for defining the connection, plus the second condition that if I take a scalar field, and if I take the double gradient of this field minus I take the double gradient in opposite order, then this is 0. That is to say, the commutator of two covariant derivatives acting on a scalar field is 0. This gives also a condition. Actually, if you write this condition in the natural coordinates that I've been using here, you find that this condition implies that this object with 3 indices must be symmetric under its 2 lower indices. So this condition here says that this object is symmetric in these 2 indices. This condition here gives a linear equation for the gamma contracted by the g equal this. And the theorem is that there exists a unique connection so that these 2 conditions are satisfied. This is called the Riemannian connection or the Levi-Civita connection. The important point is that given a curved spacetime where I don't have a connection but I have a metric g mu nu, there exists a unique way of differentiating now tensors, vectors, and company, which is defined by this recipe. And again, historically, it's an amusing fact that the connection was discovered, after the metric. Riemann had introduced the metric, and then Levi-Civita and general relativity was invented by Einstein without the linear connection, although they were the so-called Christoffel symbols, but they were realized as an abstract connection, as something which was a parallel transport of vectors, as a geometric operation of vectors by Levi-Civita after general relativity. So general relativity like predated, gauge theories and connections and all that, because it had a rich structure itself. Now,
when did Levi-Civita do this?
In 1917, if I remember well. Soon after. He was, sure. He was following general relativity, and then he introduced the connection explicitly. Okay. Levi-Civita was a geometer. The gamma symbols, okay? They had been introduced technically by Christoffel without thinking in geometrical terms. Levi-Civita was a geometer. So when he realized that this was, he wanted to understand what it means for vectors in a manifold. And I should say that actually the definition, I can give you the definition of a connection by Levi-Civita. Where is my, here. Okay. The definition of connection by Levi-Civita was the following. You take a curve manifold. Let me draw a little thing here. I have lost my, here. Let me draw it here. I have a curve manifold. Levi-Civita knew that any curve manifold couldn't be embedded in a flat manifold with more dimensions, because let's say this is a 4-dimensional, so today we would say a brane, okay, inside a bigger manifold which is flat. Now a vector at each point is something which is in this tangent space. Now you want to parallel transport this vector here at a different point here. The problem is that the vector space here is not in the same direction as the vector space here. But the definition of Levi-Civita was you take this vector, you transport it parallelly in the ambient space, which means it is out of the tangent space at the point x prime, and then you project it back. Okay, so it defines a vector at the next tangent space. And this is a nice geometrical definition. You prove it is independent of the embedding, and this is this thing. So to Levi-Civita, it was a more geometric thing. Okay. Spinors. Sorry.
That condition that the covariant derivative should commute,
Yes.
I thought that the commutator of two covariant derivatives was proportional to the Riemann tensor. So putting it.
This is true. But and I'm going to write this. But this is true where if this object has vectorial or tensorial indices, when this object has no internal tensor indices, you cannot even write a Riemann tensor. So for this case, you don't have Riemann. That's why you can impose this.
So it's important that that's a scalar field.
Yes. Very important. Yes. Now, yes. So let me write the solution, actually. I can write it here. The solution, I don't need this extra formula here. So this is the general definition of a connection. Now, you can solve these equations. And then when you solve this equation, which means that in natural coordinates, gamma is symmetric under these two indices down, keeping the third index up. This is a good exercise to find that the unique solution of this is given by the following thing, that gamma lambda mu, okay? Where remember the last index is the differentiation index, but now because it is symmetric, it's not so important if I had put somewhere, but okay. Is 1/2 of, so let me put some space. It will be, let me write the formula and then explain how you remember this formula, okay? So these conditions uniquely determine gamma to be the combination of three terms with a prefactor. So there is a coefficient 1/2. G lambda sigma means the inverse of the matrix G mu nu down. So when I have the matrix G mu nu down, I can also define, so let me say, if this index is a summation index, the inverse matrix is such that this is the identity matrix, okay? And because G mu nu is symmetric from the start, I can put also the indices in reverse here. So this G up is the inverse of the matrix G down, okay? So this is the matrix G up, which means that if I was putting this index down by the matrix G lambda, the lambda would be down and this factor would not be there. This is the way to prove this formula. You work not with this quantity, but this quantity where, let's say, you work with the quantity gamma lambda mu nu, which is G lambda sigma gamma sigma mu nu, where I take the index up and I push it down by the matrix G lambda, and then I call it lambda down, remembering that it was up at this spot here, okay? Then I have a combination of three terms. As I know that this thing is symmetric in the two indices, the right-hand side should be symmetric. And this term is automatically symmetric. It comes, because it has mu nu here, it comes with a minus sign, and sigma has to be somewhere. And the other terms are symmetric because I have two terms, and the sigma is, when you think about it, there is a unique way to write this formula if you know that the last term is this one with a minus sign. Okay, so this has defined a linear connection associated to a metric G mu nu, except that maybe I should put this down here. Except for the following fact that I have worked here in coordinates. That is to say, I was assuming, like here, that I have a manifold which is represented by coordinate x mu. And I represent also all the vectors and tensors with indices linked to these coordinates. When I change coordinates, the x mu means this thing, okay? But when you think geometrically, if I am in a curved spacetime, at each point of this curved spacetime, given a coordinate system, like for instance, given the coordinate systems, I have the vectors tangent to the coordinate lines. These are what is called the natural frame, which is often denoted like that. So let me explain a little bit this notation, which sometimes is surprising. A vector means an infinitesimal displacement. So when I have an infinitesimal displacement with coordinates dx nu or anything, I can take a derivative along the direction. If I have a scalar field which lives at this point and this point, I can take the directional derivative, which means the difference between the value of the field here and the value of the field here, at the end of the infinitesimal vector minus at the beginning of the infinitesimal vector. Which means that if I take a general vector which now is not infinitesimal but which is finite magnitude, this means I can define the directional derivative of any scalar. So a vector is also something which allows to differentiate scalars in some direction, okay? Like in hydrodynamics where you take derivatives, how is it called, material derivative along the flow or something like that. And because of this, mathematicians like to define abstractly vectors as being a general object which can act on scalars. So it's a combination of partial derivatives, and they would say this is an abstract vector, and therefore the general components V mu are the components along a certain basis, which is this basis. Okay? When I use coordinates, the natural components of the vector, I can identify the vectors associated to coordinate system by just partial derivative along the mu derivative. But once I'm in a curved spacetime, even if I have a coordinate system, and I always need to have a coordinate system, I can also at each point introduce different vectors. I can say, no, I prefer to use a better vector field instead of the one associated to the coordinates. Maybe I want r theta phi coordinates, or I want special frames. And as Cartan insisted on many times, sometimes it is useful to have, for instance, at each point of spacetime, what Cartan called a moving frame, which is repère mobile, which means a set of vectors which are orthogonal with respect to each other, that each one has a square equal to +1 or -1, and they are orthogonal to each other. Or I can just say, I want arbitrary frame of vectors which are linearly independent, but they are not the coordinate vectors and they are not orthonormal. Okay? It's called a general frame. So a general frame would be a set of vectors E alpha hat. So now I will put a hat for if I have vectors which is not the natural coordinates, just to distinguish them. They would be, I can write them this way, okay? A general frame is a combination of the natural frame, which is this. So it is defined by a matrix with an upper index mu and a lower index, which is now the frame, okay? And to say, and for instance now, if I have E alpha and E beta, the scalar product of E alpha and E beta would be G mu nu, E mu, alpha beta, for instance. If I have these two of these vectors, the scalar product between them would be given by this scalar here. And if I want this frame to be orthonormal, I would say I impose this, okay? But now I do not impose this for the moment. It's just an example, okay? A general frame. If I have a vector V, which in natural coordinates has V mu components, if I express it along this thing, I can re-express it as V alpha along this frame. So this is like ordinary geometry. If a vector can be projected on any set of vectors, independent vectors, the connection between V mu and V alpha is simply that V mu is E mu alpha V alpha, because if you replace this into this, you get this. And if you take the reverse, you get that V alpha is E alpha mu V mu, where I have defined this matrix as being the inverse of this matrix. So now I define, let's say, E alpha mu, let's put it to sigma to say sigma beta is delta alpha beta. Given a set of independent vectors at each point, which are defined by this, I can which means I give this object, I can define the inverse of this matrix, which define this, and then this gives the connection between the things. It's just simple algebra. But now, I can, here the connection was differentiating a vector along some direction mu, okay? I can now try to differentiate. Let me define the connection now in the general frame. Okay, I will just write now some formulas. I'm sorry for these formulas, but they are important for Spinor connection and for the supergravity lectures later by Hermann. And they are important also for defining the standard model, which I have not yet in gravity, that not yet finished to define. Okay, so this was the linear connection in natural coordinates. Now, if I have a frame that is, say, a set of independent vectors at each point, E beta, what is this object? This object means I have a vector field. I act on it by the covariant derivative. So I've defined the covariant derivative of a vector. But here I take the derivative nabla along a vector E mu. So this thing here means E gamma is a certain vector with a mu index up. And it means I project the directional derivative nabla mu along the direction gamma. So I take a covariant derivative along the basis vector E gamma of another basis vector E beta. Okay. And I can write the components. If I write an index nu for this object, I can compute this thing. Okay. But this thing is a vector. So a vector can be decomposed along a vector basis, like the vector basis E that I have. So this thing has some components. Okay. So I define the linear connection, because mathematicians do not introduce a special notation for the connection, the linear connection. They always use gamma. These are the coefficients of the linear connection, the same abstract linear connection as here, except that this formula will no longer be valid, if I have a set at each point of vectors, which is a basis of vectors. Okay? And it is a plus here, sorry. Yes. I define gamma this way. And once I have defined gamma, what you find is that, for instance, I will write it this way, that the directional derivative along E gamma of the components, now if I have a vector V, which as an abstract vector is V alpha E alpha, okay, as a vector, which means that this has components, if you want, V mu given by this, okay. I can now compute the covariant derivative of these objects here, okay? And you find that this is the directional derivative, okay? So that mathematician, let me introduce this notation, okay? Plus now with the same sign, gamma alpha, beta, gamma V beta. That is to say, the same formula is always valid. If I differentiate along a direction which is gamma, the differentiation index will be the last. I have a matrix acting on this thing. Okay, I have a plus sign like here. And this object denotes that this object is considered as a scalar, and this is the partial derivative along the E gamma. So this means E gamma mu d mu acting on this thing. Okay, sorry for this a bit heavy notation, but now why do we need that? We need that because of Spinors. Because I said along the various, so what are the various vector space that exist in a curved space-time at each point? An object in space-time can be a vector or a covector, a tensor, and it means it belongs to a space of vectors at this point. It can be a column of n complex number because it is an object which is in the fundamental representation of SUN, just a column of n vectors, and there will be the group SUN acting on it, or more general groups, okay? But now, what are spinors? We have seen that vectors, the group acting, when I change coordinate system, the natural group which is acting on the index of vectors is GLD. It is here. So vectors exist if I have an arbitrary set of vectors. Okay, if I give myself an arbitrary basis of vectors, a vector has components along this arbitrary set of vectors. A spinor is not something which has components in an arbitrary set of vectors at a point. In special relativity, when you introduce spinors, you introduce them always in orthogonal coordinates, in Lorentzian coordinates. And what is hidden there is the fact that a spinor is something which is acted upon by a group, which is not the group of n by n matrices, but which is only the local Lorentz group of Lorentz transformation, or more precisely, it is a group above this group of Lorentz transformation. So let me explain this. Spinors. So I want to define connection for spinors. So to define spinors, I need an orthonormal frame. I already needed that in special relativity, but a fortiori you need it even more in general relativity. This means that if I have a curved spacetime, in addition to having a general coordinate system, I need now at each point of spacetime to have a special set of vectors which are orthogonal to each other, okay? Not an arbitrary frame, but one's orthogonal. So I need a set of vectors, E alpha, E beta, such that the scalar product of these is equal to eta alpha beta. Scalar product in the sense I had written somewhere here, where you contract, so let me write it again. It means G mu nu, E mu, alpha beta. Okay, so you give yourself this structure now. And a spinor psi is something which has, for instance, a Dirac spinor is something which has an index A, an extra index. This index A will take, okay, in 4 spacetime dimension, this takes 4 values. In general spacetime dimensions, it will take 2 to the power the integer part of the half of the spacetime dimension. You know, the number of spinors, the components of spinors grows exponentially as you go to higher dimensions, which is one of the reasons why it's difficult to have a supersymmetry beyond 11 dimensions. Now, this structure, when I have so I have a curved spacetime, I have a coordinate system, which I always need, and at each point, in addition, I have a frame of orthogonal vectors. I have to introduce this frame at each point, I need to make choices, because given a coordinate system, I don't have a canonical, in general, canonical orthogonal frame defined at each point. So I can pick many at each point. I can make arbitrary rotations. If at each point, now I have, at a different point here, I have a different frame. And therefore, now I have a group which is like a gauge group, which is the group of local Lorentz rotation. Orthonormal frame is invariant if I make a local Lorentz rotation at each point, okay? So the group which is important for spinors is this group, gauge group, which at each point are the local Lorentz rotation. More precisely, under this group, E beta will vary, for instance, by E prime, E alpha prime. So when this group of local Lorentz rotation is technically represented by matrices lambda, such that this matrix is a Lorentz matrix. Okay, it is such that lambda, for instance, alpha prime beta lambda beta prime gamma. Okay, eta alpha prime beta prime is eta beta gamma. Okay? It's something that preserves, it is a matrix that preserves the special relativistic metric eta. Okay? As you know, a spinor is defined by introducing now gamma matrices. Gamma matrices, Dirac matrices, associated to a frame, are matrices, square matrices with this dimension, so 4 by 4 when you are in 4 dimensions, such that gamma alpha, gamma beta, the anticommutator of 2 matrices, is equal to twice the Minkowski matrix, eta alpha beta. Okay? So you go to a local orthonormal frame. In this local orthonormal frame, it is as if you were in special relativity locally. In special relativity, you have gamma matrices that satisfy this Clifford algebra. Okay? By the way, I am using the signature mostly plus, minus, plus, plus, plus. In this signature, there exists a Majorana representation, is a representation where for 4 dimensions and also 11 dimensions, is a representation where the matrices gamma are real, have only real components. Okay. Why, if you are in the, like Itzigson-Zuber, mostly minus conventions, Majorana representation is a representation where the gamma matrices are purely imaginary. Okay. Here, they are purely real. And this is useful in supergravity. Now, when you define, okay, so a vector, a spinor is an object which, in a sense, lives in an abstract space associated to the existence of this orthonormal frame. Now, we want to define what happens to define the covariant derivative of a spinor. What is the difference between this spinor here and this spinor here? Or technically, what is the connection that I need to put when this object here is a spinor? Okay, I will not redo the full computation. I will just define for you what is the result. So when I make an infinitesimal rotation of the local frame, this means that I consider a matrices eta alpha beta, which is delta alpha beta plus something small, epsilon alpha beta, okay? An infinitesimal Lorentz rotation. Where, and this condition means that this object epsilon alpha beta, if I raise down the index alpha by this eta, because now I'm locally using the metric eta, is antisymmetric in alpha and beta. Okay? So it's a local Lorentz rotation, which can be a rotation in space, a boost, etc. I want to know what is the rotation in the spinor space, because remember that all this issue is to think that at each point of space-time I have an object which lives in a certain vector space, and then I want to know what is the action of my infinitesimal group element on this, because this term of the connection is an infinitesimal rotation of my object in its own vector space. So what is an infinitesimal rotation of a spinor? That is a representation of the Lorentz group, in the sense that if I do successive rotations of the Lorentz group, the product of 2 Lorentz group is represented by the product of 2 spinor transformations. The result, and you will find all the reasonings proving this, for instance, in the book of Weinberg, which has good explanations about spinors. If you don't take the first edition, because there was a crucial sign error in the definition, and the definition was wrong actually, but the latest edition, this is a very clear definition. I will define now the formula I already wrote before, but now I will define it. Given the gamma matrices, I define sigma alpha beta. Maybe in order not to confuse you, let me define it immediately as being 1/2 of gamma alpha beta, where gamma alpha beta, you know, is if alpha is equal to beta, it is 0. And if alpha is different from beta, is it the product gamma alpha get gamma beta, okay? If alpha different from beta. So for instance, gamma 0, 0 is 0, and gamma 0, 1 is just gamma 0, gamma 1. This formula is often written as 1/2 of the commutator of gamma alpha, gamma beta, which is a fully correct definition. I just don't want to write it because then this formula contains a 1/4, which is a little bit surprising. This formula contains a 1/2, okay? Why 1/2? Actually, it's very simple. This is a rotation in the Lorentz group associated to a spinor. But we know that spinors rotate with an angle 1/2 of the usual angle. So this, not 1/4, you know. This thing is an infinitesimal rotation. So a spinor is something that under this rotation will rotate by, a spinor will rotate by psi prime equal psi plus, okay, because now there will be an extra 1/2, I will write it small, epsilon alpha beta sigma alpha beta psi, because you see this 1/2 is fictitious. Here I have a sum over alpha beta, and as I said, okay, now let me be careful about the indices also. This thing means the same thing as 1/2 of epsilon alpha beta sigma alpha beta. One has to keep track of the indices, okay? I always keep them in the, I always write, by the way, matrices in the form AB like that. For me, a matrix has always the upper index, and then it is acting on XB, okay? Be careful that Hermann Nicolai writes matrices in reverse, which I never understand. So why did I say that this 1/2 is fictitious? Is because this object is antisymmetric. This object is antisymmetric, okay? Also, I should have said that. This is minus sigma beta alpha, okay? So this definition means it is an anti-commutator. So this sum means actually, if you write it explicitly, this sum means epsilon 0,1 sigma 0,1 plus epsilon 1,2 gamma, sigma 1,2. So each term in the sum appears only once, okay? So it means in the plane 0,1 or 1,2 of rotation, I have a rotation by sigma, and sigma contains only 1/2, okay? Why, if you write all things, you have a 1/4 or 1/8, and then you are a little bit confused. A spinor is something that rotates, when you rotate by 2 pi, when a vector rotates by 2 pi, a vector rotates by half of this. That's why you need a 4 pi rotation to have really something. Okay, so I have defined here, given this thing, I can now write the connection of a spinor. I will write it here. Okay, the covariant derivative of a spinor, of a spinor psi. Yes, I have two. I will write it in 2 ways. Ooh la la, I was supposed to go much further than this. Okay, that's okay. So first, let me define the covariant derivative along the frame element, E gamma of a spinor. This thing means the directional derivative of the vector E gamma, which means E gamma mu d mu acting on the psi as if it were a scalar, plus 1/2 of gamma alpha beta gamma sigma alpha beta psi. I hope I put the indices correct. Yes. Ah, yes, except that here I have to put alpha down and beta up. Yes. So, given an orthonormal frame, let me summarize. I was saying that in this orthonormal frame, I have the coefficient of connection associated to this orthonormal frame that were defined somewhere. I have still this empty spot. Okay, I had written the definition of the gamma in an orthonormal frame, and I had written the formula for our vector varies. A vector varied by just this object, which is the coefficient of connection in the orthonormal frame. A spinor varies by the same, the general formula of a connection, except that this thing appears contracted by the sigma, which is 1/2 gamma alpha beta, which is the matrix T, which represents the action on a spinor of a Lorentz rotation. So when I do a connection, this means if I act on a vector, I have a rotation. The parallel transport, yes, or let me say this. The parallel transport operation from this point to this point is a rotation in a certain vector space. If it is a vector, it is a local Lorentz rotation geometrically. When I act on a spinor, I take this infinitesimal rotation that would act on a vector with these indices alpha beta, that would be the way the connection acts on a vector. But I contract the alpha beta by how a rotation acts on a spinor, which is 1/2 gamma alpha beta, where gamma alpha beta is the antisymmetric product and gamma beta, and with the same sign plus. And this is the rotation acting on a spinor, and it is part of the connection acting on a spinor. And if I want, instead of writing this projected along the direction E gamma, where I have this thing, I can also compute the covariant derivative of psi along a coordinate direction E mu, which means it is d mu psi. And here I will have something which in general it is, so there is a kind of confusion here in the literature, because this object is usually not denoted gamma. It should be, it is denoted omega alpha beta mu, sigma alpha beta times psi, okay? Where people denote this omega alpha beta mu, and they call it the spin connection. But omega alpha beta mu is not the spin connection. Omega alpha beta mu is just the ordinary linear connection where the last index is projected. So omega alpha beta mu is just gamma alpha beta gamma E gamma mu, okay? It is just the linear connection of a vector in a frame in which you have replaced the differentiation index not in the gamma direction, but in the mu direction in the space-time direction, and you give it a different name. But the spin connection is the contraction of this by this. Okay, sorry for this technology. Now I should just say that this formula, which gives the linear connection when I use coordinates, that is to say, when I don't use a frame at each point of space-time, but everything is written in natural coordinate-related frames, I need now to tell you that there exists a formula which gives the connection gamma, but when it is computed in a frame of vectors, an arbitrary frame. And I will just write the formula. And one can prove as an exercise that it is the same geometric object that I have defined geometrically. If I have, so I have defined a connection, and this form, by the way, yes. So let me write this formula also. This formula is more simple to write if I lower the index lambda by g lambda sigma, and here I put a sigma, okay? So if I call it gamma lambda mu nu, this formula just means that I have 1/2 of just this parenthesis, d mu g nu sigma plus d mu g nu sigma minus d sigma g mu nu, okay? It is an equivalent formula. I write this because the same formula if now I am in a frame, okay? If I am in a frame, I have a connection which has gamma alpha beta gamma, which has indices projected on the frame. I can lower this index.
Why did 2 in front? You actually
Sorry.
And the lambda is the sigma.
Yes, thank you for the correction. Maybe I should put a sigma here. Yes. Indeed, the 2 was to forget about this 2. Now, let me just, if I take the connection which had 3 indices in a frame, and I lower this index down, but now I work with frame indices, this is obtained by the sum of 2 terms that I will write. One term is the same as this one, okay? So, except that now the indices have changed name, okay? So, I have the directional derivative along the vector E alpha, so I write the last term first because it's the one, yeah? Alpha beta gamma, okay, plus these 2 terms, E beta G gamma alpha plus E gamma G beta alpha. Okay, so this means a directional derivative along the vector E of the coefficient of the connection, of the metric G in the frame. So now, when I have 2 vectors, E alpha, E beta, if I take the scalar product of these, this is what is defined as G alpha beta. the metric now are computed in a frame, in a local frame, where G can be eta alpha beta if it is orthonormal, but maybe it is not eta alpha beta, maybe it is a general thing that varies in space. So I have this first term, and then I have a second term, I mean 3 terms, which is the following: minus C alpha beta gamma, minus C beta gamma alpha. One must be careful about the indices, minus C gamma beta alpha, where I have a dot here, dot here, dot here. So I have 3 other terms which contains structure constants of the frame C, which are defined as follows. Given a frame E, a frame E means a vector operation of this type. Okay, I can take 2 directional derivatives in the direction beta and gamma. Okay. If you make the commutator of these 2 differentiation, a priori you should think that you will have a second order differential operator, but they simplify and you get something which is a first order differential operator that you can decompose along the frame again, and then you can define the C as being this way, E alpha mu d mu. Okay. So given a frame view as a set of differential operator, first order, if you take the commutator of 2 elements of the frame, it is a linear combination of along the frame, and this is therefore an object with 3 indices alpha, beta, gamma. If I take this object and I lower alpha by G alpha beta, I get the structure constant C down, and then I have this extra term. Okay. So this has nothing to do here with spinors. It's just saying the same linear connection acting on vectors, but possibly in a frame, is given by this formula. If you are in an orthonormal, if you are in a natural frame, only the first term remains, because in a natural frame, these operators are just d mu d nu, and these d mu d nu, they are 0. So it means the structure constant C for a coordinate frame are 0. So this term is 0. Only the first term remains, which is this one. If I am in an orthonormal frame, the G alpha beta is constant, eta alpha beta, and therefore these derivatives are 0. So the first line is 0, only the second line remains, and this defines the connection in a frame. And when I have a spinor, you take a frame, so this term is absent, you can compute the connection this way, then you plug the connection with this formula with an extra mu in the derivative of a spinor. Okay, so here I have at last fully defined what is the way gravity couples to a spinor. So I can go back. So I have defined my last term.
I'm supposed to imagine hats on the right.
Yes, here I was, for simplicity, yes, dropping the hats after a while.
And Thibault, shouldn't all the C's appear with minus signs or the first one with a plus sign?
So I've just changed, I have put the last one, that's why there's a minus. And the other ones, they all know the second line, okay. The second line, it depends how you write it. This object has 3 indices and it is antisymmetric with respect to the last 2. Because of this, you can change signs in many ways. But there is a way where it has the same sign and then the thing is a permutation. That's one I prefer because it's alpha, beta, alpha, gamma, beta, alpha. This way, you write indices by permutation and then you find there is only a minus sign.
Yeah, except that you didn't write it as the cyclic permutation.
Ah, sorry.
The last one is not.
Gamma, thank you. Let me check. Gamma, beta, alpha. Ooh la la. I hope I copied correctly now. I have here gamma, beta, alpha, which I have copied somewhere on my notes. I think it is correct. I mean, this is the delicate things.
It's correct, but it's not cyclic.
It's not cyclic, yeah, sorry, which means I made a mistake in the previous sentence, okay? But I think it's, okay. These signs are delicate, okay? And there are books even where they are wrong, okay? I know somewhere where they are correct in some of my notes. They will be correct in Hermann Nicolai's lectures. But be careful that the differential index will be placed somewhere else, which makes things confusing. So all this was to say, in the standard model we have fermions. these fermions couple to gravity. The coupling to gravity now, besides the fermions contain gauge couplings, and then they contain this extra term, and now I have defined everything here. I said, for the fermion, I need, in addition to coordinate system, to have a frame. This frame, in this frame, I have gamma matrices, gamma alpha, gamma beta. I define the rotation of a spinor in this, and then I have this object that often people call spin connection, but it is just the connection acting on vector. It's the linear connection. Last thing. Yes? 5 minutes. Yes, 5 minutes. So I will, just a piece of information. When you write the Dirac action, I did not define psi bar, by the way. So let me define psi bar, because in this signature, the gamma matrices are real, but you know that the usual definition of psi bar in the Dirac conjugate is psi dagger times beta, okay? And beta in the usual Dirac thing is gamma 0, but it's gamma 0 when you are in the opposite signature. When you are in this signature, there is an I, because you want a Hermitian matrix. And therefore, the gamma 0, when you are in the mostly plus signature, is anti-Hermitian. The spatial gammas are Hermitian. So I gamma 0 is Hermitian, and this is the one you want to define in psi bar. So there is a hidden I that you need absolutely in the Dirac action, because there must be an I, psi dagger, psi dot, okay? And this is the way you get it.
Because also, I think the gamma mu disappear in favor of the gamma A, right?
Yes, so I was doing that at some stage. Now, if you want, because first I wanted the d mu here, okay. When you define the thing, then you also introduce a frame here, and you take not the mu derivative, but the mu derivative projected along alpha, so it's the alpha, and everything now is defined in the Dirac action. So the summary of this is that the first postulate of general relativity is now defined. There is a universal minimal coupling of gravity to the standard model, in the double sense that algebraically everywhere the special relativistic metric, when it appeared here algebraically like here, is replaced by g mu nu, and all the derivatives that appear in these terms have been replaced by these covariant derivatives, nabla mu, which was very important when acting on fermions. I said when it was acting on the gauge field, there was a curl, and now you can find as an exercise, because of that nabla mu a nu minus nabla mu a mu is equal to the ordinary curl because of the symmetry of the gamma lambda mu nu when you are in mu nu indices. So this was a way of seeing why I did not need here gravitational coupling. Okay. So I will go to the second postulate of GR next time. Okay, good. I stop here.